Today we're doing limits and continuity in multivariable calculus. And we can start with some relatively easy examples just to kind of get warmed up. I'm labeling these easy, but limits in reality are almost never easy. They look scary if nothing else. We could start with a problem like this. What is the limit as well? Since it's a multivariable calculus function, a function of two variables, we need to consider letting two variables approach two different values. Written as a point, say x comma y approaching some other point with some specific coordinates, maybe pi over 3 comma 2. So what does this mean? It means x is approaching pi over 3 and y is approaching 2 simultaneously somehow. But that fact that it's approaching, x is approaching pi over 3 and y is approaching 2 simultaneously has some shades of meaning that are not completely obvious at first glance or at first thought. We need to think about what that really means. But what is the function here? Let's make the function be, how about sine of x times y plus y cubed times, let's go ahead and do y cubed times x. So there's my function of two variables, f of x, y. If I asked you, is this a nice function of two variables? I hope you'd say, it doesn't involve dividing by 0 evidently anywhere, and it doesn't involve square roots of negative numbers. The domain of this includes the entire plane. X and y can be any point in the plane. Nothing too weird is going on. I hope you remember from Calculus 1 that in computing limits of functions like this where nothing too weird is going on, you probably can just plug in the numbers. And that is the case. We can just go ahead and plug in these numbers. X is pi over 3, y is 2. So we get sine of pi over 3 times 2 plus y cubed is 2 cubed times x times pi over 3. That is the limiting value, but you should be able to simplify this. Okay, think with me here. Remember your trig values. Pi over 3 radians is equivalent to 60 degrees. So 2 times that is equivalent to 120 degrees, just past 90 degrees there. Sine of such an angle is the second coordinate, which is close to 1. Of the memorized values, this should be square root of 3 over 2. Square root of 3 over 2. That's what ultimately sine of 2 pi over 3 is. And of course, this simplifies to 8 pi over 3. So you could write the answer as square root of 3 over 2 plus 8 pi over 3. Make sure you double check my work to make sure I don't make a mistake. If we get a common denominator of 6, we could also write that as 3 square root of 3 plus 16 pi all over 6. Let's double check it with a calculator. Okay, sine, make sure we're in radian mode. I am in radian mode. Sine of 2 pi over 3. Yep, that looks like square root of 3 over 2. Plus 8 pi divided by 3. Oops, not times. Plus 8 pi divided by 3. Looks like the limiting value is close to 9.2436. If you wanted to double check that you simplified it correctly, double check that I simplified it correctly here, I could do 3 times square root of 3 plus 16 pi, all divided by 6. Looks good. Okay. What's going on here geometrically? Let's use Mathematica to make a plot of this and also review our plotting of multivariable functions here. So f of x, y is this function, this example here. Use a capital S for the sine function, x times y plus y cubed times x. Should put a star in there. You can put a space, but just as a default, it's good to put a star. Of course, I could also type that as x times y cubed. Let's go ahead and plot this. A plot 3D will give us the ordinary plot as a surface. I could plot it over a big window to start with, like -5 to 5, relatively big, in both directions. What are we going to see? Again, we're seeing a two-dimensional surface inside three-dimensional space. Talked about this last time. As x and y vary over the entire plane, different points in the plane give you different outputs, different z coordinates. The graph consists of ordered triples, x, y, and the corresponding z. Since the plane is a surface, that's why we get a surface in general here. It's a little bit of a wavy surface, maybe not too surprising because of the sine function in there. Though probably as x and y get big, that term there kind of dominates. And probably as we go out further, you would not necessarily see much wobbling. We see it kind of close to the origin here, but probably it would not occur as we go out further. Another kind of plot we can make is a contour map. Copy and paste this code to save a little time. Instead of plot 3D, do contour plot. If you don't add any options, I think the default number of level curves, it might be 10 or 15 or something. Maybe even fewer. 1, 2, 3, 4, 5, 6 here, it looks like. We can add in more by doing contours arrow and then add in however many level curves you want. Like 50 is a lot of them. Nothing too strange looking going on here, but realize how to interpret this. It's like you're looking down at a map, a contour map where these lines represent elevation. And lighter shading corresponds to higher elevation, higher outputs for the function. So the function is higher up here, and you can see the individual outputs. I don't know how big those numbers are for you. The cursor kind of gets in the way, but I see 130 there is what I see for that number. Also relatively high over here. Then darker shading represents lower values. Relatively low down in here, like -210 is what that says, and lower over here. What are we letting x and y approach again? We're letting x approach pi over 3, which is a little bit bigger than 1, and y approach 2. Some point right around here is what we're approaching. That contour has output value 10. This contour has output value 20, it looks like, hard to see. Remember that our limiting value for this thing was the function value at pi over 3, comma 2. There it is exactly. It's approximately 9.2. That's close to this level curve where the output is 10. In this graph, we're letting x approach pi over 3, y approach 2 is sort of underneath the graph. The height of the graph near there is close to 9. If we want to see the graph better, see if there's any oscillation going on near the origin better, it'd be good to restrict the plot range in the vertical direction. Oh, maybe just from -2 to 2 or something. To maybe see some oscillation, or maybe a little bit bigger. Okay, we're seeing a little bit of oscillation there, but even close to the origin, the y cubed times x term is kind of dominating. So you don't see much oscillation beyond a little bit of waviness in there. Okay. So that's an example of a relatively easy limit that you can compute just by substitution. What official property are we using to allow us to compute this by substitution? Does anybody know the name of it? Starts with a C. What's the official property? Go ahead and say it loud. I think you said it right. Close. Continuity. There we go. This function is continuous everywhere. Its graph, that surface, doesn't have any holes in it, doesn't have any jump discontinuities, no breaks in the graph. It's continuity that is allowing us to evaluate this limit by substitution. You can say a little bit hand wavy. This is not a real precise definition. Basically, a function f of xy of two variables is continuous at a point P with rectangular coordinates x naught comma y naught if the limit as a variable point xy approaches P with coordinates x naught comma y naught of f of xy equals the function value at x naught y comma y naught. That's the key equation. Okay, basically that's what continuity means. Now there are some subtleties that I'm putting under the rug. Like, what's the domain of this function? Is f of xy even defined near this point? It depends on what the domain is. I'm also, the bigger thing is I'm kind of shoving under the rug is, what does this limit really mean? Let's get into a little bit of depth on that. If the point P is right there, what does it mean to let your arbitrary point xy approach P? Does it mean approach it along a straight line? Or can it mean maybe approach it along some wavy curve? Or can it mean approach it maybe even along some spiral? Wouldn't that be fun? Could we let xy approach P in those different ways? Or maybe another question is, should we allow xy to approach P in those different ways? The answer is yes and yes. We can let xy approach P in those different ways. And in fact, we should allow it to approach P in those different ways. Infinitely many directions of approach and infinitely many curves of approach. Oh, that seems a little bit overwhelming. In one variable calculus, you just let x approach some number either from the left or the right. Just two directions. Here we got infinitely many different directions, even if we only restricted ourselves to lines. But we also have infinitely many curves. And where in the world is xy to begin with anyway? I mean, I drew it right there, but it could have been somewhere else. That is making this idea, this multivariable calculus limit, harder to get our minds around. Examples will help. But again, the easy examples, we just do by substitution. We also can note, this is worthwhile to do as well, that in doing this substitution, we also could have thought of it as applying some other properties of limits. We've got a limit of a sum, for example. Notice where I'm pointing? A limit of a sum of two functions. We could have thought of that as the sum of the individual limits. Formally speaking, I would be using this kind of property. The limit as xy approaches x naught comma y naught of the sum of two functions, f of xy and g of xy, equals the sum of their individual limits. Now, this is a lot to write, but it's worth writing at least once, I think. However, in writing this equation, I'm really making an assumption to say this equation is true I'm assuming these individual limits on the right exist in the first place, right? If I'm going to say the limit of the sum is the sum of the individual limits, as an example of one abstract property, I better know that these individual limits over here exist. So I'm really assuming these exist, assuming these exist in order to write this in the first place. But if you make that assumption, you can say this is true. Likewise, you can generalize this. The limit of a difference, f of x minus g of x, is the difference of the limits. I won't bore you by writing it. It's in the book, right? That's worth me not writing because it would be boring and we got other things to do. But you should know it's true, and you can see it in the book. If I changed it to a product, the limit of a product, f of x times g of x, is the products of the individual limits, assuming these individual limits exist. If I changed it to a quotient, the limit of f of x divided by g of x would be the limit of f of x divided by the limit of g of x. Wait a minute, is that troublesome? Well, maybe L'Hopital's rule applies to a 0 over 0 indeterminate form, or maybe in that case, if I was saying the limit of a quotient is the quotient of the limits, I have to worry about dividing by 0. What if the limit of g of x is 0? Maybe I'd need L'Hopital's rule, or maybe the limit would not exist. So yes, you'd only want to say the limit of a quotient, f divided by g, is the quotient of the limits, the limit of f divided by the limit of g, as long as the limit of g, even if it exists, is non-zero. Okay? Again, all these things are important. They are technically useful. A couple of your homework problems are purely abstract problems. No formula for f and g, but you need to use these properties to get the right answers. Okay? They are worth emphasizing to some degree. What about harder examples where maybe substitution doesn't work? Maybe we need to use L'Hopital's rule, in fact, or maybe we need to use something else. I've got in Mathematica some harder examples. Tricky limit problems. Maybe the limit will exist, maybe it won't. Let's see what happens. Let's take a look at this example. You might want to write it down. F of xy equals 3xy all over x squared plus y squared. First of all, what's the domain of this function? And in talking about this domain, I'm also going to start talking about some of the terminology at the beginning of section 12.2. In particular, some things called open disks and open sets I'm going to talk about here. Maybe I should write by hand here as well. For this example, f of xy is, as you see, 3xy divided by x squared plus y squared. What's the domain of this function? What values of x and y am I allowed to plug in? Well, as long as I don't divide by 0, I'm fine, right? And that's only going to occur at one point, the origin, because x squared plus y squared is always strictly positive, bigger than 0, if I'm not at the origin. So the domain D of this function consists of all points xy in the plane R2 that are not the origin, such that xy is not equal to 0, 0. Can you read this as the set of all points x comma y, ordered pairs, that we can visualize as the two-dimensional plane R2. The R emphasizes that the coordinates are real numbers. The vertical line can be read as such that, or with the property that, X comma Y is not 0, 0. We're not at the origin. If you're going to draw this domain, well, people would typically put an open circle at the origin and like shade everything else. That domain has an important but subtle property. No matter which point you are at, whether you're here or here or here, or maybe even really close to the origin, but not equal to the origin, there is some disk, in fact, infinitely many disks, centered at the point that I picked, that is entirely inside the set. For example, with this point, this disk is entirely inside the set. Certainly any smaller disk centered at that point is entirely inside the set as well. As long as I don't make my disk too big to include the origin, the resulting disk would be entirely inside the set. So about the limit of how big I can get with the disk is about like that. I don't want to get much bigger than that to make sure the disk, all the points inside there are still inside the red shaded region, which includes the entire plane except for the origin. And that's true even if my point was really close to the origin, there is going to be a small disk centered near that point that's entirely inside the set. When that happens, when your set, your domain in this case, consists of points at which you can find disks, possibly very small disks, that are entirely inside the set, they're centered at the points, then we call the set an open set. This domain, D, is an open set. It's a two-dimensional analog of an open interval or a union of open intervals. If you think about an open interval on the number line, like that, no matter where you are inside this open interval from A to B, even if you're really close to A or really close to B, there's going to be some small interval centered at the point. Even if I was really close to A there, some small interval centered at that point that's going to be entirely inside the interval. That does not happen with closed intervals. A closed interval from A to B, like this, including the endpoints, has the property that if you're at the endpoint, one of the two endpoints, there's no open interval centered at that endpoint that's going to be entirely inside the set. It's not an open set. Okay? I'm going to draw later some generic pictures of open and closed sets that are analogs of open intervals and closed intervals. This is just the first little introduction to it. This function is undefined at the origin. However, it's possible that even though the function's undefined at the origin, the limit as you approach the origin might still exist. That does happen sometimes. You've seen that before in Calculus 1 as well. Think back to Calc 1. Take a function like sine of x over x. That's a function that's undefined at the origin, x equals 0. But its limit as x approaches the origin does exist, even though the function's undefined there. You can use L'Hopital's rule here. This is a 0 over 0 indeterminate form. Both the top and the bottom are approaching 0 as x approaches 0. So according to L'Hopital's rule, if you take the derivative of the top and the derivative of the bottom and then make a new fraction like this, if this limit exists, then this limit will also exist, and then they'll be equal, according to L'Hopital's rule. And this limit definitely exists. That's a function that's continuous everywhere. You can plug in x equals 0 and get cosine of 0. The limit is 1. This function, sine of x over x, it oscillates and approaches 1 as x approaches 0, even though the function's undefined there. If you graph it, it's got a hole in the graph at 1 when x is 0, but it's continuous everywhere else. So the limit as x approaches 0 does exist, but the function's undefined there. It's not a continuous function at 0. though it is sort of a weak kind of discontinuity. We could remove that discontinuity by just filling in the missing point, couldn't we? It's called a removable discontinuity, because if I just make a piecewise function, f of x to be sine x over x when x is not 0, and 1 if x is 0, then I've created a continuous function. But the point still holds. The function doesn't have to be defined at what you're letting x approach in order for this limit to exist. So once again, coming back to this example, it's possible that the limit of this as I approach the origin exists. It's also possible it doesn't exist. How do we start to explore which is it? Does it exist or not? Let's go ahead and make graphs to start with. We'll make plot 3D and a contour plot again. So I'll just do some copying and pasting here. Here's the plot 3D. Looks sort of ordinary, except something weird's going on near the origin there. Looks like it's like folding on itself or something. Let's try zooming in closer to the origin and see if it becomes more pronounced or not. Not really any more pronounced. Maybe I should do a plot range -1 to 1. That's looking kind of weird. Isn't that weird? What in the world is going on there with that function? What does the contour plot look like? Oh, wild. Now remember, each one of these curves, which seem to be straight lines here, correspond to different values of the function. Lighter meaning higher, darker meaning lower. If we approach the origin here, it seems like the function approaches many different values. How could we confirm that? Let's approach the origin along an arbitrary line, call it y equals mx, where m is an unspecified slope. Could be a positive slope, could be a negative slope, could be a 0 slope. I'm not going to take an infinite slope, though I could approach the origin along the y-axis, which would be a vertical line. You could maybe say with infinite slope, but I wouldn't want to use this equation if I did that. How do I think about this? How do I imagine approaching the origin along such a line? Go back to your formula up here and replace y with mx. Think of m as a constant, x is a variable, but you're wondering, does the constant m affect the answer? If it doesn't affect the answer, then that might be some evidence, though maybe not a proof, that the limit does exist. If m does affect the answer, then the limit can't possibly exist, because it would mean approaching the origin along lines with different slopes gives you different answers. That's what the picture seemed to indicate. Probably the limit is not going to exist. In the formula, go ahead and replace y with mx everywhere you see a y. Should I stop there? No, keep simplifying. Simplify as much as you can. On the top, it simplifies to 3mx squared. On the bottom, it simplifies to x squared plus m squared x squared. Can I simplify more? Yes, I can, as long as x is not 0. I can factor out an x squared out of the bottom, and then I can cancel the x squareds, divide them out, to get 3m over 1 plus m squared. Something that depends on m. Seems like the answer depends on m. It seems like the overall limit must not exist. You might wonder, though, is it valid to cancel the x squareds? I mean, this function wasn't even defined at the origin anyway. These are equal as long as x is not 0. But, you know, in the end, we're letting x and y both approach 0 anyway. So is there a problem here? The answer is no. Because remember, with limits, it doesn't actually matter what happens to the function at the point. Just like back in this one-dimensional example, it didn't matter that this function is undefined at x equals 0. Doesn't matter. Completely irrelevant for whether the limit exists or not. The function's not defined at 0. Doesn't matter. The limit exists and still equals 1. The original graph had a hole in it. I filled in the hole by making a piecewise function. Can't always do that. If it's got a vertical asymptote, you're not going to be able to. It's that kind of discontinuity. That's called a removable discontinuity there because I could fill in the hole. Likewise, it's completely irrelevant that this function is undefined at 0, xy equals 0, 0, or that this one's undefined at x equals 0. I'm just letting x approach 0 without actually equaling it. And again, I'm saying I get different values depending on what m is. Therefore, the overall limit as xy approaches 0, 0 of 3xy over x squared plus y squared does not exist. And don't try saying it like equals infinity or negative infinity here, because it doesn't have a vertical asymptote, okay? In the 3D graph, we saw some sort of weird folding going on with the graph, indicating that something weird's going on. And in the contour plot, it's a little bit more clear. Along any line through the heading toward the origin, you had different shading, light versus dark, different output values, different limiting values. So the overall limit doesn't exist. All right, the next example is even a little bit stranger. Now our function is sine of x times y over x plus y. Let's once again think about it, some things by hand first. For this new example, f of xy equals sine of x times y divided by x plus y. We should once again think about the domain. Domain's a little bit trickier here. You still want to avoid dividing by 0, so you can still pretty quickly say the domain must be the set of points in the plane, R2, with the property that I'm not dividing by 0, so this means x plus y does not equal 0. But as far as understanding what that domain is, it's a little trickier. You need to realize this is the same as the inequality y does not equal negative x. It's equivalent to that. So if you're going to draw the domain, you want to consider all the points in the domain except the points on the line y equals negative x, which goes to the origin with a slope of negative 1. So if you're going to try to draw it, I mean, this is a little bit misleading, but you might try to draw sort of a dashed line in a thin vertical empty strip with a slope of negative 1 through the origin and shade everything else up here and down there. However, in drawing it like this, realize, right, I've made it look like what's not on the domain has some thickness to it. It doesn't. It's just a missing line. The line y equals negative x. All the points on that line y equals negative x are not in the domain. All the points not on that line are in the domain. This is an open set as well. No matter where you are, here, down here, 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 as long as you're not on the line y equals negative x, there'll be some disk centered at the point that's entirely inside the red shaded set. It has to be a smaller disk as you approach the boundary of the domain. But it is an open domain. D is an open set. This terminology about open sets is going to be important for us, not really so much for this assignment, though it is in the reading. It's also worth pointing out that both of these domains for these last two examples, the last one was everything in the plane except the origin. This one's everything in the plane except the line y equals negative x. Both of these domains do go off to infinity, so to speak. We say they're unbounded. This is unbounded. Bounded versus unbounded is going to be important for us as well. Not so much today, but later. Introducing the idea today. A bounded domain doesn't go off to infinity in any direction. You can put it inside some possibly very big disk, and it's completely inside there. Unbounded means it goes off to infinity in some direction or another, or maybe in every direction. Those would be examples of unbounded sets. So once again, we're going to let x, y approach the origin here. We're wondering what's the limit as x, y approaches the origin of this function, sine of x times y divided by x plus y. Again, let's just get a little feel for what might be happening with technology. So I enter the function, I try to plot 3D. Oh boy, looks kind of weird. Looks like I've got some sort of higher dimensional vertical asymptotes, perhaps. If we zoom in closer to the origin, we see less waviness, but we still see some sort of vertical asymptote, it seems like. Maybe not. It's hard to tell for sure. But although, you see some things going up seemingly forever and ever, perhaps, no matter which one of these that you look at. However, near the origin, it's actually a little bit tamer. Near the origin, it seems like maybe there's not a vertical asymptote. That's this spot in here. It did put like a little bit of a space inside the graph, a hole. I mean, the function is undefined at the origin. What's the contour plot look like? Oh, wow. Isn't that pretty? Let's try fewer contours. What, 20? Okay, doesn't look too much different. Wow, very pretty graph. What's going on there as we approach the origin? The origin's right there. Okay, let's try what we just did in the previous example. Try approaching along some line, an arbitrary line, along y equals mx. What does this function equal along a fixed line y equals mx? I have to replace y with mx. Think of m as fixed, a constant. So we're imagining approaching the origin along some fixed line. And we're wondering what happens to this function along that line. Oops, this should be an x here. Replace any y with m times x. So I get sine of x times mx over x plus mx. Sine of mx squared divided by, you could factor out an x is it necessary. That's not so clear. X times 1 plus m. And I could ask, well, what is the limit of this as x approaches 0? For the two-dimensional function, for the multivariable function, that would correspond to approaching xy approaching the origin 0, 0 along a line with slope m. Is it clear what this is? Does this limit exist? We could try L'Hopital's rule. It is a 0 over 0 indeterminate form. Right? Both the top and the bottom are approaching 0 as x does. Sine of 0 is 0. So we could try L'Hopital's rule. With L'Hopital's rule, it's always a little funny because you're never quite sure if it's going to work. L'Hopital's rule is always true, but it's not always helpful. Let's try it and see what happens. So I take the derivative of the top. with respect to x, I get a cosine mx squared. I need the chain rule. I get an extra factor of 2mx. And the bottom, differentiate that with respect to x, I get the constant 1 plus m. Oh, guess what? As long as m is not -1, this limit exists and equals 0 because of the x there. If m is not -1, oh, -1 was that line y equals -x, where the function wasn't even defined in the first place. So that's not a problem to assume m is not -1, right? Y equals -x. There's a line through the origin where the function was undefined, not part of the domain. And so effectively, I am assuming m is not -1 here anyway. I'm not approaching the origin along that line. So this limit exists no matter what m is, and it always equals 0 no matter what m is. So what do we have here? Is that a proof that the overall limit exists? Does this limit exist and equal 0? The answer is no, because we still haven't considered approaching the origin along curved lines, curves. Maybe, well, I guess we can't do it around spirals because that would go across the line y equals -x. And in fact, this is an example in the book. I'm doing examples in the book today to reinforce the reading. If you approach the origin along a certain curve, y equals negative sine x, the limit will not exist. Really? Well, what does the function equal along that curve y equals negative sine x, which, by the way, if you graph it, will look like this. In the xy plane, that's the curve y equals negative sine x. What does the function equal along that curve? I have to replace all the y's with negative sine x. It was sine xy on top, so I get sine of x times negative sine x, and then it was x plus y in the bottom, so I get x minus sine x. The limit of this thing as x approaches 0, through various work involving L'Hopital's rule, you'll see in the book, does not exist, actually. Crazy. It's in the book. You can look it up. I'm not going to go through the details. This is in the textbook. It's kind of a nasty L'Hopital's example because you got like signs within signs here. So taking the derivatives gets a little nasty, and you get some, yeah, I think you maybe even have to apply L'Hopital's rule twice. So that makes it even more nasty. But what you find is it doesn't exist. Is there a way we can believe that here? Probably the best way is to just graph as an ordinary plot, the plot of f of x times x comma negative sine x near 0. That's probably the best way to believe it. Ordinary graph. Yeah. Looks like vertical asymptotes. How do you relate this ordinary graph to the higher dimensional graph? It's tricky. In the contour map, I would try to plot negative sine x. It would be a graph that looks like this, and it would cross where the well, it's not, no, it only crossed the line y equals negative x at one point at the origin. The white region here, by the way, it is defined for most points in this white region. It's just high in value, either positive toward positive infinity or negative infinity. The graph of y equals negative sine x sort of approaches the white region, and it ends up meaning that the outputs approach, well, plus infinity, it looks like, when x is approaching 0 from the left, and minus infinity as x approaches 0 from the right. In the 3D graph, can we see that? Yeah, as you're approaching 0 sort of along this way, you're kind of heading up this piece right here. to positive infinity. And as you approach zero from this direction, you're heading down this piece. That's intuitively why, for the higher dimensional picture, we're failing to get a limit. So you have to consider more than just lines, is the point. So it seems like for these examples, these weird examples, that the limit just doesn't typically exist. But that's a misimpression as well. Because the next example, this one, the limit does exist. Does this limit exist? The answer may surprise you, but I'm telling you the answer. It does exist. Write down this function. 5x squared times y squared divided by x squared plus y squared. Even though this function is undefined at the origin, the domain includes all points but the origin. Set of all points in the plane with the property that it's not at the origin, which is once again an open but unbounded set. And whereas the previous two examples, the limit as we approach the origin did not exist, here the limit as we approach the origin does turn out to exist. As x or y approaches the origin from any direction, whether a straight line or curve or a spiral, as long as we don't go through the origin, this limit exists and equals 0. Let's see if the technology helps us believe it. Let's plot this right away close to 0. Yeah, the graph looks pretty ordinary. Nothing too strange going on. Seemingly no folding. Technically, it is undefined at the origin. You don't see a hole in the graph. In reality, there would be a point missing. Contour plot. It's interesting looking, but it is tame, you might say, near the origin. Dark region in a plus sign near the origin. In fact, if you're along either the x or y axes, where both of these expressions are 0, the fact that you're dividing by something and getting closer to 0 doesn't matter. And here, Daniel, your idea about the degrees affecting things does matter. Ultimately, the degree of the top of this polynomial, this rational function, is the sum of these two powers. 2 plus 2 is 4, and the degree of the bottom is 2. And ultimately, the degree of the top being higher than the bottom is enough to guarantee this limit exists as 0. But you might ask, how do you prove that? It's hard. Let me give you a little feel for how to prove it without actually proving it. This is related to the official rigorous definition of a limit involving some Greek letters epsilon and delta that maybe you saw in Calc 1 and maybe you didn't. Intuitively, we're saying the values of this function can be made as close as you like to 0, as long as x comma y is close enough to the origin. As long as x and y are both sufficiently close to 0, no matter which direction you're approaching the origin. The difference, let me call this 0L as a common letter to use for a limit value. The key thing is to focus on the absolute value of the difference between the function and L. And the question is, can I make this as small as I like by making x and y close enough to 0 simultaneously? Because the absolute value of the difference of two numbers, and these are both two numbers here, represents how far apart they are. When this absolute value is close to 0, then the numbers are close together. And when the absolute value of this difference is large, then the numbers are far apart. Well, I'm claiming L is 0 here. So I can replace the L with 0. And subtracting 0 has no effect. So I can just say it equals this. And as long as we're not dealing with x and y being imaginary numbers, these are all positive quantities, also as long as I'm not dividing by 0. So I can actually, for this example, get rid of the absolute value signs. So it doesn't feel like we've done much. We've verified that for this example, the absolute value of the function minus the limiting value that we claim is the truth, L equals 0, is the same as the function itself. And remember, I want to make this as small as I like, less than any given epsilon. I want that to be true, no matter how small epsilon is, as long as x and y are close enough to 0. How in the world do you verify such a thing? It's often, especially in examples like this, through a little bit of trickery, a little bit of sleight of hand, you might say, or thinking about things in the right way. In this case, it's good to rewrite this as x squared times 5y squared over x squared plus y squared. I still want that to be true. And the key here, after you do this little trick, is to realize this quantity, and this is why I separated off the x squared, this quantity right here, never gets bigger than 5. Right? Because if I didn't have a 5 there, it'd never get bigger than 1. I've got a quantity, y squared, divided by that same quantity, y squared, plus some other positive number. That's got to be less than 1. And therefore, if I multiply it by 5, it's got to be less than 5. This is less than 5 over the entire domain. So effectively, it's almost like this is equivalent to saying that's true. Almost. I'm just doing an intuition here. So wanting this to be true. And that's equivalent to this being less than epsilon over 5, which if you take the square root of both sides is equivalent to the absolute value of x being less than the square root of epsilon over 5. And that's typically called delta. So what's really going on here is if you want this to be true, if you want to make this distance less than any given number epsilon, no matter how small, intuitively, you can choose x to be within this distance of 0, because this is the same as the distance between x and 0, and that'll happen. This will be true. And this being true basically also can be guaranteed by saying that the distance between the point xy and the origin is less than delta. Draw a picture here. Here's the origin, 0, 0. Consider a disk of radius delta centered at the origin there. If my point, the D here represents distance, if my point xy is within a distance delta of the origin, meaning it's inside this disk somewhere, then certainly x itself will be between negative delta and positive delta, the x coordinate of that. So if I assume this is true, where delta is epsilon over 5, that'll mean this is true. And ultimately, it's going to mean this is true. You will find this argument in the book stated in a bit more rigorous way than what I did. I was trying to give you just some intuition here. This is the kind of thought process that needs to go into verifying that the limit truly exists. Guess what? That's really hard. We don't usually want to do all this, right? Who wants to do this stuff? Not many people. I mean, pure mathematicians kind of like it, but most other people don't. Pure mathematicians often want to do this, but not many other people want to. So what do we do? How do we get around this conundrum? We use properties of limits, which I already talked about. And hopefully those apply to most of the problems. Or we use the analysis that we did for the examples where the limit did not exist. Consider approaching along various lines and hope that the limit doesn't exist, because that'll be enough to prove that. Or along some curve, maybe based on a hint. The curve we used for that example was y equals negative sine x, but that's not obvious that that curve is going to work. For continuity, we use properties of continuity. Got two continuous functions? If you add them, it'll be continuous. If you multiply them, they'll be continuous. If you subtract them, it'll be continuous. If you divide them, they'll be continuous as long as you're not dividing by 0. All those things that you would hope would be true are true. The rigorous approach, to tell you the truth, is not really so much necessarily for particular examples as it is important for proving the properties that you hope are true. Okay, we don't get into those kind of details. We're just trying to get a little feel for what's going on through examples.